Camera operation is the first standard in the series of standards that you need to know for broadcast video. Camera operation has seven objectives in the standard. Objective 1 is basic parts of a camera, where we have the image sensor, the lens, the body, and the viewfinder. Most people know lens, body, and viewfinder, though there's more to the lens than the common person knows. We do know that, like in eyeglasses, it's a piece of glass that bends light. There's a lot more to it that we'll learn during this slideshow. But the image sensor is something that a lot of people don't know a whole lot about. Let's start just by understanding how a camera works, how it picks up the light and images and turns it into something that we can view in a digital format. The DSLR camera, DSLR stands for Digital Single Lens Reflex, and sometimes you'll just hear Single Lens Reflex camera. In a DSLR camera, the light passes through the front lens or a series of lenses. It goes through, the light passes through there, bounces off a mirror that sends the light up in a 90-degree angle. The mirror is at 45, so it shoots the light up and passes and bounces off a series of mirrors that will send that analog image through the viewfinder. Now, an analog, using the term analog, let's look at it in terms of opposite of digital. Analog is something that's in the physical world, and digital is converted into digits. It's literally digits, zeros and ones, on, off. But that explains something to a computer that in turn gives an output so you can see the image. So you're turning the actual physical light that is passing through, you're changing it when it hits the sensor into a digitized format. And how that does it with a mirrored camera, you see the light that's bouncing off that 45-degree angle mirror. That mirror flips up. If you're just going to take a single image and you press the button, that mirror flips up so that the sensor can capture it. Now, in a mirrorless camera, it doesn't have a mirror. The light goes straight towards the center, and the sensor captures and digitizes the image, which it will send to that digital display, that teal little bar up on top. The digital display is what you're seeing when you look through the viewfinder. Here we're going to talk about, this is a little video about CCD versus CMOS image sensors, and we'll talk a little bit more about it after the video.
Hey there, I'm Courtney Cox-Darquette, lead camera person on set. This camera here is one you're likely to see in any production studio you visit. The way this camera works is pretty simple. Light enters the camera through the lens, that light then hits the charge-coupled device, and then converts the light information into an image. Now, inside of the body of this camera, there are actually 3 CCD sensors. There are 3 because to be able to process and redistribute color information, it has to measure light at 3 separate wavelengths. That's 1 for each primary color, red, green, and blue. So in order to do this, a prism block is used to separate the image being captured into the reds, the greens, and the blues. Because of how the prism is assembled, each of the 3 colors gets its own charge-coupled device. That means the CCD is able to devote all of its pixels to that particular color channel. An advantage to using CCD is the resolution. Even though a CCD sensor uses a lot of time and energy converting each pixel, it can hold a large amount across its surface. However, a downside to CCD is what's called the blooming or smearing effect. This happens when a light-gathering pixel exceeds its capacity to hold captured photons. That excess spills over into the adjacent pixels and can produce a spike of light in the image. There are other options when recording video. For instance, the cameras you use to record Snapchat videos on your cell phones uses a CMOS sensor. Though they record less resolution than a CCD, CMOS won't cause blooming or smearing. To get a better idea of what CMOS sensors are, meet Charles at the CMOS Institute.
Hello, I'm Charles Moss from the CMOS Institute, and today I'll be talking about CMOS sensors. Let's get started. CMOS, which stands for Complementary Metal Oxide Semiconductor, is the sensor that can be found in most cell phones, web cameras, and DSLRs. Let's look at how these sensors work. First, light enters through the lens and is directed to the CMOS sensor. A primary color filter sits on top of the sensor that divides the light into red, green, and blue. The sensor converts the light into an electric signal, which is then in turn converted into a digital signal. This signal then carries and imprints images on whichever storage device is being used. CMOS sensors generally work faster than CCD sensors and require less power to operate. They are also cheaper to manufacture and more compact, making them ideal to include into consumer products. Another advantage of the CMOS sensor is that because they capture each pixel individually, they don't have the same blooming and smearing problem that CCDs have. One of the main drawbacks of using CMOS sensors is what's called the rolling shutter effect. They scan images the same way we read books, moving from left to right, line by line. This creates problems when trying to capture fast-moving subjects or panning the camera while shooting, as it can create a distorted and inaccurate representation of what is being captured.
Okay, so, so that last part that you saw there, I just duplicated it here so you could see it on the slideshow. You have two types of image sensors, the CCD, which is a charged coupled device, and the CMOS, complementary metal oxide semiconductor. Here's the pros and cons of each of them. The CCDs are used in broadcast cameras. It's in our broadcast cameras in our studio. That's what we're using, and we use that because it has a better image quality. Also, if you know what you're doing with the camera and you're in a controlled atmosphere, you're not going to be too worried about the downside, which is that susceptibility to the image blooming or smearing. That blooming or smearing is basically it's overwhelmed by the light, and you saw that vertical band of light spread out. There's various forms of that, but it's essentially it's a problem that causes this burst of light on your image. Whereas the CMOS doesn't necessarily have that problem. It's cheaper to make, faster, and it's used in the cell phones that we have, the web cameras that we use, the DSLR cameras, but it is susceptible to that rolling shutter when it's scanning from left to right, remember, and you have a fast-moving object, you might see some sort of distortion based on that rolling shutter. One other thing actually that I want to add here, and this is something that's not in the slideshow here, is the term demosaicing, and I want you to write that down, type it on your cell phone, write it on a piece of paper, type it on your computer. Demosaicing, first of all, let me go back to actually color. We're going to learn more about color theory. When we're dealing in the visual world on computers and digital cameras, and light, if we're talking about stage shows, plays, our primary colors when we talk in terms of that are red, green, and blue. That's RGB. As opposed to the color wheel that we saw in that last video, you'll see that the primary colors form a triangle in the world of paint, which is red, yellow, and blue. So know that the difference, if you're using paints, you mix yellow and blue, you'll get green. You mix yellow and red, you get orange. In the world of light, green is a substitute for yellow for complicated reasons which we won't get into, but RGB in the world we're talking about here. Now, demosaicing, what it does is it takes these colors and the middle term of that, mosaic, you might recognize from the art world where they take tiles. They even do this sometimes in bathrooms where you have a tile, but it actually creates a picture, not just like white, blue, white, blue, white, blue that I have in my bathroom, but in the world of artwork, in the ancient world, they might have created floors or walls out of these mosaics where it's little squares side by side in 2 dimensions, and it creates a picture. So think about that word mosaic. And to demosaic, what it does is it's a computerized world of interpolating colors or interpreting colors. When colors come through and are captured by an image sensor, it might not be capturing the actual true world color. So it's a program that says, I'm going to take this color and infer what it really means. What I'm the analog world that I'm receiving, I'm going to infer what it actually means in the digital world, and that's called demosaicing. Let's jump onto lenses here.